Alright, right now we're going to take a look at a logistic differential equation, which is helpful when you're looking at population growth that has a carrying capacity. So if your population cannot grow without bound, bacteria can often grow and grow forever at an increasing rate, exponentially. But most populations cannot. Food scarcity becomes an issue, predators, etc., etc. And so there's often a carrying capacity, a maximum, which a population can reach. And so our differential equation has to be a little bit different. So we'll use P as our population, all right, and then I think L is what we use for the carrying capacity. All right. Now before, our differential equation was the change in your population with respect to time was proportional, K, to the population. So the bigger your population, the faster the growth. However, with carrying capacity, we add something to that. So what we add here is 1 minus the population over the carrying capacity, L. Now what that does is, as your population gets closer and closer to your carrying capacity, so as your population gets bigger, this whole fraction gets closer and closer to 1. So let's say your population was 4,000, but your carrying capacity was 5,000. That's getting awful close to 1. And as your population gets closer and closer, or that fraction gets closer and closer to 1, these parentheses get closer and closer to 1 minus 1, which is of course 0, which means your change in population would be getting smaller. So as your population gets bigger, the change in the population actually gets smaller, which makes some sense because that would mean you can't get past your carrying capacity. This population of 4,000 would not be growing very fast because its maximum is 5,000, so it would grow very slowly. Whereas if the population was only 100 and you could support 5,000, well, that population could grow quite quickly still. Alright, that's a little introduction of where this formula comes from. Let's do some math with it. So here is our differential equation one more time. The change in the population with respect to time is equal to some constant K times our population times 1 minus P over L. And so our goal is to take the integral of both sides here, but before we do that, we have to separate our variables. We're going to get all the P's on the left and all the T's on the right, even though there are no T's. So multiply by dt to both sides, multiply by dt on both sides, and then it looks like we're going to divide by P times 1 minus P over L to both sides. Divide over here also, I'm not going to write it. You can if you want to. So what we're left with then is 1 over P times 1 minus P over L dP equals, on the other side we just have a K dt. Hopefully you can see how it does look similar to what we've been doing before. Now we're going to take the integral of both sides. Now that we've separated our variables, we can take the integral of both sides. The right side is not too hard. That is simply kt plus c. That one's nice and easy. The left side, however, is not easy. You can't use a simple u substitution for this one. We are going to have to use partial fractions. We've learned that already. We're going to break this up into two integrals. One integral dp plus another integral dp. And they are both going to be fractions. Now that's going to take a little bit of doing, so I'm going to do that over here. So we need to break this fraction up into a over something plus b over something. And so the first factor there is p, and the second one is 1 minus p over L. And those will then be our two integrals. So this is a nice simple partial fraction in some ways, so we have to figure out, we can use the shortcut. So first, you figure out what makes this one 0. Remember, p is our variable, so p equaling 0 will make this one not work. And so we're going to cover up this p and plug in 0 to the other p. So I'll hold the red cursor over there. If you plug in 0 for p, 0 over L is 0. 1 minus 0 is 1. And so you simply get 1 over 1, which that is our first a value. A is equal to 1. Alright, now we have to do b. So what value of p makes this denominator equal to 0? Well, we have 1 minus a number here. If p is equal to L, you'll have L over L, which is 1. You'll do 1 minus 1 is 0. So p cannot equal L. That's the number that makes this one messed up. So L is what we're going to plug in for p over here. Alright? So, let's see if I can do this. We'll try this out. So we're going to cover up this part right here. So imagine that's gone. And into here, we're going to plug in L. So that'll get you 1 over L, essentially. So B is equal to 1 over L. So let's plug those in now. A is 1, so this is going to be 1 over P. And B is 1 over L, so you'll have 1 over L on top. And on the bottom, 1 minus P over L. And that's a little small there, isn't it? Let me make that a little bit bigger. So that one will be the integral of 1 over L over 1 minus P over L. Alright, so we broke up the partial fractions. Now we can actually take these integrals. So we'll take the integral. The first one is easy. 1 over P is simply the natural log of the absolute value of P. Plus the next integral. This one's going to take a little bit of doing. I'm going to rewrite this one more time because this L can actually be moved down into the denominator. And so what that's going to look like is this: 1 over L times the bottom, 1 minus P over L. Alright? Well, now you can distribute that L, and when you do that, this L in the denominator will get canceled out. So we have the natural log of the absolute value of P plus the integral of 1 over, let's see, L times 1 is L, minus P. dp. Which that integral is now much easier to take. It's a fairly simple u substitution. Alright, I'm going to put my natural log of the absolute value of p again. Don't want to forget that. Here I'm going to make u equal to L minus p du is equal to, here you have to remember p is our variable, not L. L is just a number. So that is going to be -1. So instead of having a plus, we're now going to have a minus because of that du. Natural log, since this whole thing down here became a u, it's going to be the natural log of what u was, L minus p. And we took both our integrals. Now you have to remember, I've got some chicken scratch here. This whole thing equals, still on the right, kt plus c. Alright. Now our whole goal here is to get p by itself. Oftentimes it was to get y by itself, but this time we have p and t instead of y and x. So we need to get p by itself. One step that isn't obvious the book does here, it multiplies both sides of the equation times -1. It makes things a little bit easier later on. So this will become negative kt plus c, and then this one will become positive and this one will become negative. So I'm going to rewrite that as natural log. I'm going to switch them. Sorry for my bad handwriting there. Alright, now we can use the property of logs. I'll come back over here. When you have logs that are subtracting, you can write them as one natural log, but you turn them into a fraction. L minus p is on top, and on the bottom you have p. It's kind of a nice property of natural logs. On the other side we still have negative kt plus c. Now we can take e to both sides, so that you're left with L minus p over p is equal to e. I guess technically if we multiplied this by -1, that should be minus, shouldn't it? So should that one. It doesn't matter too much because that c is just a constant. It's going to be coming down here anyway, so I'll put that there right now. E to the negative kt. Alright, and we're interested in population. So we're going to solve for p. Now we've done all the calculus. That was pretty rough. But now we want to get p by itself. That way we have an equation for our population. Population equals something. So we're going to multiply both sides times p. So that cancels out. So you have L minus p, it's a subtraction sign, equals, I'm going to put the p in front, p times c times e to the negative kt, and then I'm going to add p to both sides. Hopefully you can kind of see how I'm going to get p by itself here. So we're left with L equals p times c e to the negative kt plus p. Now I can factor out a p. Alright, plus, you factor out the p, you get 1 equals L. And now we can divide both sides to get p by itself. So as you can see, we're going to divide by all of that, so that our population will then be by itself. L will be on the top, and on the bottom we're going to have c e to the negative kt plus 1. Pretty brutal. One other thing, for some reason we stopped using the letter C and we turn that into the letter, your book at least turns that into the letter B. It doesn't really matter what variable you use oftentimes. And then it's addition. They may, I think in the book they switch these. Not too big a deal. But that gives you your general equation for population. Remember, L is the carrying capacity. And P is the population. Alright? So that kind of walks you through how that integration works. That will hopefully set you up for the next problem.